Now we have a basis B for a vector space consisting of the vectors 3, 4, and negative 8, 6. These vectors are orthogonal. They have a dot product of 0, as we can see here. I'm going to call these vectors V1 and V2. So let's see, just put V1 here, V2 here. I've got it here too. Okay, and we're going to assume that these are eigenvectors. 1 with eigenvalue 2, V1 with eigenvalue 2, V2 with eigenvalue negative 3. And by familiar, what's familiar by now? The transition matrix, the transformation matrix relative to basis B then is just a diagonal matrix with the eigenvectors, eigenvalues on the diagonals. And then the transition matrix from basis B to the standard basis is just a column of eigenvectors basis, a column of eigenvectors matrix. So that if we have a vector represented with respect to basis B, we multiply by the column of eigenvectors basis, and we get the vector as represented with respect to our standard basis. And then if we want to go from A to B, of course we're going in the opposite direction. We multiply by the inverse of that matrix. We've done this many times, so this should be quite familiar. And the A matrix then, the matrix relative to our standard basis, we start in A with a vector. We move it to basis B with the inverse of our column of eigenvectors matrix. Then we transform it according to the matrix, according to the matrix A sub B, this matrix, diagonal matrix, and then we bring it back to our standard basis. So we multiply the vector by this, then we multiply by the diagonal matrix, then we multiply by the column of eigenvectors basis. And that gives us our matrix A. Now, what if we want an orthonormal basis? This is an orthogonal basis, but it's not an orthonormal basis. Okay, well, to make this an orthonormal basis, all we have to do is make all the vectors unit vectors. So we simply take the vector 3, 4 and divide by its magnitude, take the vector negative 8, 6 and divide by its magnitude, and this basis will be an orthonormal basis. Okay, and that orthonormal basis will be, well, we do the calculation easily. The magnitude of 3, 4 squared is, the 3, 4 dotted with the 3, 4, which is 25. And then I say, okay, the magnitude of 3, 4 is therefore the square root of 25 or 5, so that when we multiply our 3, 4 matrix, looks almost like I wrote 2, 5. Anyhow, multiply our 3, 4 vector by 1/5 to make it a unit vector. We get 0.6, 0.8, and that's a unit vector. Similarly, 8, negative 6 has a magnitude of 10, so we take 1/10 of 8, negative 6, we get 0.8, negative 0.6. This is also a unit vector. They're still orthogonal. We haven't changed their directions, and you can verify that the dot product is still 0. So, we have an orthogonal basis, we make it into an orthonormal basis, and we put this in the context of eigenvectors. And we'll see where that is really quite an important context. Okay, we'll continue.